A very warm welcome from our side here from Schlotau and Bauer to a new webcast. We are really happy that you joined us today.
Welcome to this webcast, Adaptive Network Control, in particular MYCITY Adaptive. INES is now mainly marketed as MYCITY Adaptive, but that does not mean that our existing INES projects will not be supported as those or that development has ceased. It's just that this webcast in particular has more of a focus to explain the control algorithms to everyone who's not familiar with them. Nothing has changed there. So if you've seen our recent webcast regarding INES, there won't be anything new there for you. But in the end of the webcast, we want to highlight those features or synergies that we can offer for those customers who want to work with the MYCITY Adaptive / INES algorithms out of a MYCITY environment, in particular the MYCITY Cloud, and we'll have a look at what we can offer there. So we're going to start with motivation. Why do we do adaptive control? Then we're going to talk about MYCITY Adaptive algorithms, a short interlude with results and references, like taking a look again at the Bogotá project that we finished 2 years ago, because that is the one where we have a very good database to actually show results, measurements, what are the effects of our adaptive algorithm. MYCITY Adaptive modules is about what different software packages or pricing packages are we actually offering. And as I said, the last but not least part, MYCITY Adaptive Cloud Solutions. And then, of course, Q&A at the end. Motivation, philosophical approach towards adaptive traffic control. Why are we doing it? Our goals are, of course, improving the user experience or improving the traffic situation and avoid congestion, reduce travel times, improve safety by minimizing waiting times and stops, environmental considerations. Low traffic means less emissions, less energy consumption. Also efficiency, not only from energy consumption perspective, but also from a perspective like what is efficient from the perspective of a city, of how do we use existing infrastructure in a meaningful and sustainable way. And we look at what an adaptive traffic control should do. We have a little network here, like really high level, kind of showing what's going on in the morning. Why do we need a morning peak program? Because we see a traffic pattern that is mostly having traffic into the city, and then vice versa, evening peak traffic, where we have the majority of road users going out of the city again. So our adaptive solution should ideally not only have an answer for that, but also recognize those patterns automatically and react accordingly. If we're thinking about a control algorithm, the basic problem that we are facing is that the more capacity we are offering in the signalized intersection, the more potential waiting time we might also cause for secondary direction. So what we are looking for is actually the sweet spot between just as much capacity as necessary, as opposed to also as little capacity as possible, because that will also reduce the waiting time at the same time. So that is the basic idea or the basic goal, or what we have to achieve, the solution that we have to come up with. How do we do that? So we come to the MYCITY Adaptive algorithms. First thing we should have a look at is what different modules do we have? What different layers of control does MYCITY Adaptive offer? And we can see that it's basically two main layers. One is the scenario selection, kind of the basic algorithm that is always coming with our installation, a scenario selection, meaning we have a library of programs or scenarios for a certain area or a control area that are selected by our control algorithm. It's doing this by looking at the actual situation right now, looking at a short-term prognosis, how is traffic actually developing right now, which capacity do we need for the current and developing situation. And once we've assured that the capacity is enough or adequate for the traffic volumes, we're looking at the coordination, deciding whether or not a direction should be prioritized, which pattern does actually fit the coordinations that we have at hand that we can offer. And on top of that, strategic detection. Do we have any alerts, any congestions that suggest that we should maybe change the plan that we have just made because something unforeseen has happened that we're detecting with these strategic detectors. That's the basic algorithm. We will have a closer look at all these steps in a minute. The second layer to that is green time redistribution, meaning that the central layer is also providing guidance for the local control in terms of maximum green times, so changing the green time split and the offset in the same process. So if we go through this step by step, first things first, short time prognosis. Why are we doing a short time prognosis? Why are we not doing long term? Short time meaning projecting the next 5 minutes of the current situation. Our argument has always been a long term prognosis would probably always be based on historic data. So basic understanding is that you have to have for when you're optimizing with an adaptive solution, how much can you actually rely on these historic data? This is an example where the red line that we see here is representing the average Monday. On this particular situation, you see that on this day, the whole traffic pattern is shifted by half an hour. So the blue is the actual traffic that we were measuring that day. Green is our short-term prognosis, which is quite close to what we're actually measuring. Historic data that tells me that traffic should actually only arrive in 20-25 minutes is not really helpful because I have to react now. The demand is already there. And on the other hand, if you would imagine the situation being the other way around, like our historic data shows an uprise at, let's say, 7 a.m. and in the real world, it's only happening at 7:20. You might argue, well, that's fine. I already changed to a higher capacity program at 7 a.m. because I'm anticipating that traffic will come and then it's just there 20 minutes later. These 20 minutes are actually where the potential for optimization is lying. Once the peak hour traffic has arrived, this is usually using all your infrastructure, all your time that you have of your maximum capacity programs, but where you can actually optimize and give people the benefit of an adaptive solution is in this dynamic part where you don't know when traffic actually will start. If you are not reacting as closely as possible to the current traffic volume, then you could actually go again with use a scheduled control because everything that you have to put in as safety is actually optimization potential that is not used. So a long story short, short-term prognosis, because of course, if there are changing conditions, we want to know in which direction are they going. We maybe need a little safety capacity wise, but anything further than 5 minutes for us is actually not really helping. So the algorithm, what is it based in? We're basing our decision on the flow ratio or saturation of the signal groups in the network, saturation being the ratio between the needed green and the actual green. So if you have 20 seconds that you really need and 30 seconds that you have available, you would have a saturation of about 66%. Actual green, in this case, not always what was actually activated in the street. If we have a traffic actuated traffic adaptive control, then usually it ideally should cut at these 20 seconds anyway, so you would end up with 100% there. Actual green always meaning the potential green that would be available if all flows would go for the maximum green time in that specific program or that specific scenario. So the saturation is something that we're calculating out of the given data. But the saturation alone will not give us a sufficient criteria to actually decide when to change from one scenario to the other because, well, saturation in itself is not a measurement for quality. If you just say, okay, let's keep the saturation low so everyone has enough green time, when you do that, you're actually not in the sweet spot anymore of just having that green time that everybody needs because you will end up with cycle times that are always at the maximum. So there is a lot of unused green time, which we do not want. On the other hand, if we're just saying, okay, then let's maximize the saturation, let's always use like 100%, maybe 120%. So that also doesn't work because then we have oversaturation and we're producing tailbacks. So what we need is something that always finds this sweet spot, this middle ground where we can define a perfect range or a corridor of saturation. And that is what we're doing with this utility function that is at the core of our decision processes, where we define an ideal saturation corridor. In this case, would be something between 55 and 70%. So this is the scale that you've seen on the slide before. And this green area leading to a high utility score of 100%, whereas in these other areas, it's declining when we're not in the ideal range. And also, as soon as we see that this maximum saturation, which in this case is something like 90%, is broken, then we're going to deem a scenario or program as inappropriate or as not usable in that given situation. So this is what we're doing for all signal groups in the network at any given time for the current situation and for the projected situation or projected traffic volume. It's resulting in something like this. You have a low capacity plan, which also might have a different utility curve. In this example, we have a volume of 150 vehicles per hour, and we're having a look at, okay, what would that mean in a low capacity plan? That would mean something like 50% saturation. In a high capacity plan, it would probably just be 30% for this particular signal group in this scenario. And that will mean we have 100% utility in the low capacity plan and only 50% utility in the high capacity plan. So the low capacity plan would be chosen in this situation. Maybe this is a chance to look at how this would actually look in an actually MYCITY installation. So this is MYCITY Adaptive. If you are used to the INES control panel, so you have the control panel and with the scenario selection parameters. So this is where you can put in this utility parameter. You have headway and weight factor for all the different signal groups. And then with this curve you set, you can go into the actual situation that we're having right now. So this is the average situation in the network. These are all the signal groups that are defined in this particular network. And you can see we have color-coded the current saturation. But as I said, this is evaluated when you go back to this slide, not only for one plan, but also for all available plans or for all available scenarios. So we're going to have a look at the utility that is resulting from this volume. So in the background, MYCITY Adaptive knows all the green times in all available scenarios for every signal group, and it's evaluating them. And here you can see everywhere where you see a red bar, that means that this particular scenario is currently oversaturated or not eligible for a certain signal group, whereas the green color means that this is actually in particular program perfectly saturated. So usually to calibrate such a control, you go with these, look for the point where it breaks down. So here is the point where the utility curve for the day program breaks down. And then 5 minutes later, the control would definitely go to a peak program. So, and if you in the calibration process would realize, okay, this is happening a bit too late, a bit too early, all you have to do is go into this scenario parameters and change the maximum allowed saturation for this particular program. And that's a short version, of course. If you want more information, you can probably set up an additional meeting. So let's get back to the algorithm. This is step one, of course, which we now call the capacity optimizer. So optimizing by choosing the solution that has the best or optimized capacity available for the current situation. And then in the second step, what we're doing is evaluate the coordination. Imagine a situation where on paper you have two programs. One is the morning peak program, the other is the evening peak program. They are not actually different in the green time per se for each intersection for the main direction, but the offset between them is designed in such a way that one situation you have perfect coordination going outbound and one situation going inbound. And of course, what you have to do is see under the current load on the network, which of those is actually producing or leading to a smoother flow. And therefore, we are evaluating the lost time that is generated by vehicles passing through the coordination in both directions. So this, when you look at where the green bars are, so the green time we assume is the same here now for both directions. In reality, we would look at both directions separately, but just for the sake of the example, it's literally the same, just to show that this coordination is significantly worse for the opposing direction. So here we have a lot more lost time being accumulated. And now we not only do this for one vehicle, but we do it for all the vehicles, and also looking at tailbacks. So waiting time that is generated by waiting for another vehicle to actually make way is also taken into consideration. You look at that here in the lost time. So these are the lost times for the programs that are available here on this in this network, and you can see that they're kind of dancing around one another. So sometimes you have the green when it's getting denser, then the green curve is actually has a higher lost time, and vice versa. So this will then lead to a decision between these two programs, like morning peak and late peak. So far for steps, we have taken a look at the volume and the prognosis. We have taken a look at the capacity. We have evaluated the coordination, calling it offset optimizer, looking for the optimal scenario offset-wise. And then in the last step, we're going to double check our results with the strategic detection, because everything we've done up until this point is simply based on the number of cars that we're detecting, the number of vehicles, taking into account their expected time gaps and so on. But of course, in certain areas, you will find congestion tailbacks that cannot just be detected by simply counting vehicles. If you look at this kind of cloud here of combination between the volume on the x-axis and on the y-axis we have the speed, and you have, okay, higher speeds or higher volumes lead to slightly lower speeds. But when we look at the next slide, at some point you're getting to a critical area, and if traffic actually breaks down, you're getting data points where with low volumes you have low speeds, and that is because there's actually a lot more demand, but just cannot be met by the available capacity, or there might be other influencing factors that have caused the traffic to break down. So in this situation, just by looking at the numbers, in this situation, this data point here and all the data points up here, they will lead to the same saturation, will lead to the same assessment of a certain scenario, and maybe even lead to the result, okay, we have very little traffic here, so maybe we change to a lower capacity program. But seeing that the speed that is actually driven here is so low, we would reassess that decision and say, okay, we cannot go to a lower capacity program right now because there is something critical happening. Yeah, that's the whole purpose of speed detection and strategic detection. So what's the outcome then after all this calculating back and forth? Capacity, lost time, strategic detection. We have a decision for a certain scenario, which would look like this. Let's look at a whole day. So in this graph, you see blue dots for the decision made for a certain scenario by the algorithm, and green for the actual scenario being active outside on the street or out on the street. So that is why you have a single blue dot and down here a single green dot. So in this particular interval, there's the decision made to change to the scenario P3. So it's still active on the street, but the recommendation is a different one. And in the next interval, you can see that it's then actually activated. So this giving as a feedback, not only the decision, but also did the controllers in the street follow suit. And if you look at the tooltip, you can also see the individual controllers being in that particular program. So much for the scenario selection or the basic algorithm, say offset optimizer or capacity and offset optimizer. Then we have the green time redistribution, where we change the green time split and change the offset, both functionalities that actually require the local control to implement a certain API. How it works in our approach that we have implemented in Lisa with OMTC controllers is that we're actually using permission plans or permission periods, which act as timeframes where a stage is allowed to end. And we, by manipulating these timeframes at runtime or optimizing these timeframes, the control is redistributing the green time, which should also appear up here in English and not in German. Sorry about that. So don't make the mistake if you understand now that the adaptive control is actually dictating every second of green at the local level. This is still done in the local controller, but the green time redistribution is done on a strategic level. So the maximum green time that can be used within the local control are being controlled by the adaptive green time redistribution. A short detour, results and references. If you followed this webcast before, you will probably recognize this as also as the explanations I gave before. So Bogotá, capital of Colombia, we did a replanning of all 1,500 intersections. Redesigns were necessary of the control. All of them got new intergreen times, and all of them were assessed whether or not they should be part of an INES control network or INES control zone / MYCITY Adaptive. Of course, there it's implemented as INES, but as I said, the control algorithms are exactly the same. All these yellowish areas represent an individual INES zone. Some of them, as you can see, are simply coordinated corridors. Some of them are meshed zones, and depending on the dynamic of the traffic in a particular zone, it was decided on an intersection by intersection basis. Does it make sense to just do scenario selection, which is called responsive mode here, or to do green time redistribution, which is called fully adaptive in this case. And it's put here in kilometers, but it's 800 controllers in total that are actually controlled by the network control, because it was a limited amount of video detectors. So we also had to decide to run some intersections strictly on a scheduled in scheduled mode. These are all these single dots that you can see on the map, and about 300 of them are actually running in fully adaptive mode with green time redistribution, and 500 of them are run in responsive mode, which also can mean that they run traffic actuated, but it's their green time is not touched by the green time redistribution is not touched by the network control. What were the results? If you have in mind that some adaptive controls will tell you, well, we have a 30% in journey time improvement. We have this also in some areas. The average that we were reaching was about 10% among all measured corridors. In some, it even went worse, even worsened the situation. But I mean, you have no control about the measurements. I think these are expected outliers. Also, if I would tell you, okay, 45%, this is the usual improvement. Also, nobody would believe that. But yeah, if somebody is telling you that he can do 20, 30% easily, then I would not trust that person. So yeah, we achieved that in some cases, in some not, but I think 10% overall is already a pretty solid number. Also, given that Bogotá is not an easy case, very much oversaturated and highly congested city that really has capacity problems that cannot be solved with traffic lights alone. Lost time improvements. These are lost time improvements that we calculated within the software, comparing the plans that were originally planned or scheduled, meaning when you look at the schedule and you have where you have all these, we cannot take into account unforeseen traffic patterns, and where you always have to put in safety margins, so you're always hitting the right capacity. That is what we were comparing here. What lost time we have gotten as a result in the schedule, what lost time did we have with our decision. And if you know Bogotá, or just for explanation, there is a mountain range here to the east of the city. So these sectors 7, 8, 9, these are actually the center of the city, and all the others are the outer parts of the city. So this might explain why you have more improvement on these outer areas, because this is where the radial connections are, like cities, streets going into the city and out of the city, whereas in the center there's not so much that you can actually win in this comparison, because all the programs are basically not that much directional. So long story short, this shows how well the control is picking the right coordination, and of course there is more to win when you have really different coordinations in the plans that you have at hand. So much for results. Let's take a look at the modules once again. I mean, you have in mind scenario selection and green time redistribution. What are the different implementations currently available? Of course, there is still INES, the INES network control. As I said before, it's still supported, and also until MYCITY Adaptive Standalone is really a thing that is readily available, also something that we distribute and will give away to new customers who have a standalone server or who have an existing infrastructure with a traffic central and a process data server. How does this translate to MYCITY? So what is INES network control is now MYCITY Adaptive within the MYCITY environment. So all the communication, process data, and so on is within that environment. And yeah, for the future, MYCITY Adaptive Standalone will work like the current INES. It is actually a MYCITY implementation, just having some of the needed infrastructure to run the adaptive inside. When we're coming to functionality, what are the different packages? We have standard and advanced, or scenario selection and green time split. 90% of the time, a scenario selection will probably suffice to improve your situation, especially if you already have traffic actuated controls at the local level. The green time split is something like the cherry on top, but it also, in most cases, as a requirement that the controls are done in Lisa, or at least that they implement our API, which enables the control to receive certain runtime variables. This is defined in the OCIT interface. So if you control can implement that, then it's fine, then we can work with that. Otherwise, of course, always recommended to use Lisa as a tool for the local controls. Now for the last chapter, which I already mentioned in the beginning, MYCITY Adaptive Cloud Solutions. And this is something that is really benefits that really come from the fact that we have now not only INES as a standalone solution, but MYCITY Adaptive integrated into the MYCITY environment, which also means that MYCITY Adaptive, like MYCITY itself, can be moved to the cloud. So when you're hearing cloud, you might say, why should I move my stuff in the cloud? I want my data where I can see it. I can understand that approach. Still, I would just like to steer your attention to some of the benefits that this might have, and especially with MYCITY Adaptive, especially if you already have a cloud solution. So it's not really my job to convince you that the cloud is the perfect solution. I just want to show what you can do if you already have a cloud, which might be quite interesting. So these are the different implementation options that we have for MYCITY. One is, on-premise. So if you say, thank you, I really enjoyed your arguments regarding the cloud, but I still want everything on my dedicated MYCITY server in my city network, and I will take care of it, then this is your solution. And then there are two different cloud options. I know IT expert, so if you want to know more what the difference is between private cloud and public cloud, get in touch. As you can see, the public cloud is something where we're actually accessing your city network over the internet. So all of the software is running in our cloud server, in our virtualized environment, somewhere on a Swarco server, and then connecting to your infrastructure via the World Wide Web, whereas in a private cloud, you have something like your own cloud somewhere inside your protected area. So depending on what your safety prerequisites are, requirements are, you might choose one of two of those once you've decided for a cloud. So in general, what are the advantages of a cloud solution? Single support partner for entire IT chain, ability to test new features, and this is the point where we're getting to. Dynamic upgrades of existing functions, dedicated tech ops and IT security team, minimize reaction times in case of security risk, and so on. Data geo-redundancy, infrastructure architecture for big data volumes, easy access from any location, and of course, cost efficiency. And not only for us offering it, but also for our customers using it. So you're always having the latest version running on the idea is always having the latest version of the software running on the best hardware without you having to take care of it. Okay, fine. Something you might say, okay, this is in an ideal world, but I'm not really convinced what is the real benefit for me. This is where I'm trying to get to. So if you're already having MYCITY in a cloud, or if you're interested in MYCITY in a cloud, so the marketing team of MYCITY is also offering this to customers who say, okay, I want to try your cloud solutions, but I'm really just want to see if it's something for me. Then what they're offering is, well, you can connect 1 or 2 controllers to MYCITY, and then you can see all the maintenance and operational features and see if it's to your liking. And then if you don't like it, then connect the controllers back to your own system after 2 months or so. The same we would do for MYCITY Adaptive. I mean, of course, MYCITY Adaptive takes a little bit more of configuration for a little network, but that is what we would throw in for free for you, especially if you're already running MYCITY Adaptive. Then, or if you're already running MYCITY, that is, in that case, as long as we're having access to the system, I would even say it doesn't even matter if it's on-prem or in a cloud. Then we would just configure a few controllers because they should already be there, and then you can run the control for a few weeks or for a few months and take a look at the results. We would not actually have it send commands to the street, but you could see what it would do, and then it's your decision to either buy it or not. So I would strongly encourage you to get in touch if you're interested in that. Yeah, so that is actually the added features. I hope your takeaway is not that, or I hope your takeaway should be, okay, there are new possibilities or new opportunities, but we're not shutting any doors only because the name up here in the corner is changing. To sum it up, INES in general, MYCITY in general, MYCITY Adaptive in general, a transparent solution with comprehensible decisions and transparent algorithms, effective calibration, you have few and understandable number of parameters. It's not thought of as a black box. It should be something that a trained user can easily get their head around. And yeah, modular, flexible. Also, our pricing now, if you say, I don't need green time redistribution, a plan selection is fine, then this will also be reflected in the pricing. And what's also always reflected in the price is that these adaptive licenses are always on an intersection basis. So you don't have to buy this huge application that can, and you're already paying for what it might do, you're only paying for what it's doing now. So yeah, license and price model always based on the number of intersections. And yeah, open and vendor native interfaces supported. Of course, you won't get these nice cloud-based benefits if you're running it in parallel with a competitor, or but it's still built around open interfaces, and it should still interface with your existing infrastructure if you're using OCIT protocols. So that's basically my presentation.
Okay, so for the next events, we have some free webcasts left till the end of the year. All our regular trainings are done now in English, but the next year will be there, and you can always ask for individual trainings if you are a few more colleagues that want to have one or the other training exclusively. So yeah, the free webcasts, we have still Lisa Click Along, in October the 12th, where Mayuk Sika, our trainer, will lead you through all the LISA modules and features. Then we'll have also for LISA the CITS library on the 14th of November. So for all the webcasts, no prior registration is necessary. So feel free to just join, and we will send out participation links, and we will also publish the links on our website as we did today as well. Thanks a lot for joining us today. And as always, we are at your service if you have further questions. Please contact us at service@schlotauer.de if you have any technical questions, or if you want a quote, an offer, have any sales-related questions, then please contact us at lisa@schlotauer.de. Thanks and have a nice day.